All right, so we know we have ionic bonding occurring in any specific case. Now we want to think about what our formula is going to be. So it's not always that you have one of each, one cation and one anion. You might not have one of each. It might be a different scenario. So again, let's draw a little staircase. And let's take a look at some examples. So first we'll take a look at sodium and chlorine, how they combine. So we have Na with it's one electron, chlorine with its 7 electron. And so what we can tell here pretty simply is that, the Na has an extra, the chlorine is missing one. So they're just going to combine to form Na plus Cl minus, right? In this case, I haven't drawn all the dots just for simplicity. Let's take a look at a different compound though. Let's take a look now at potassium and then sulfur, and let's see how they combine. So potassium being in group 1 has 1 spare electron. Sulfur being in group 6 has 6 valence electrons. And so what we can tell with the potassium is that we have essentially 1 extra electron that it would like to get rid of to have that filled outer shell, whereas sulfur is 2 short of an octet. So it needs to have 2 electrons, right? And so if the potassium has 1 and the sulfur needs 2, we're going to need 2 potassiums for every 1 sulfur. So for example, what that would look like is we could have a K plus, and then our filled sulfur with its -2 charge now, and then another K plus. Another way that you can write this is 2K plus, and then the sulfur, right? They both represent the same thing, but you can see to have an overall neutral charge, you need 2 potassiums for every 1 sulfur. And then of course we can write the formula for this. So we write this as K2S, where the 2 is a subscript. So it's that kind of small number. And what it tells us is the number of that atom in the formula. Right, so it tells us that there's 2 potassiums for every 1 sulfur. And overall, these are relatively simple for the most part, but sometimes they do get a little bit complex. Let's take a look at an example of that. So here we have this aluminum, and in this case, aluminum has 3 valence electrons, and then we're going to combine it with oxygen, which has 6. And now we've got to combine these two so that they both have filled outer shells. Well, think back from our previous discussion. We know that aluminum is going to want a +3 charge, and then oxygen is going to want a -2 charge. So in order to figure out the final formula, what we can do is a little trick here. We can just take this number right here and make it the subscript for oxygen, and then take this number here and make it the subscript for aluminum. So in this case, it would be Al2O3, right? And you can always double check it, right? Make sure everything is correct. The aluminum, each aluminum is going to have a +3 charge, as we previously learned, and there's 2 of them. Each oxygen is going to have a -2 preferred charge, and there's 3 of them. And so if you add up those 2 numbers, you'll get 0, which is equal to the charge of the compound itself, which is neutral. So that's a quick little trick. You can also think about, lowest common multiple, or just kind of logic your way through it. With this little trick, there's just kind of one thing to be careful of. So for example, when you have magnesium combining with oxygen, magnesium wants to be 2+, oxygen wants to be 2-. So according to this trick, it'd be Mg2O2. But what we need to do is we need to have the lowest numbers possible, right? So they're both divisible by 2. And so we could reduce this down to just MgO, right? You want to have the subscripts be as low of numbers as possible, but they have to remain whole numbers, right? So in the case of 2 and 3, right, you can't divide one by the other. So that's the lowest number possible. And so that's how we predict the formula of our ionic compounds. And this stuff is, pretty much spot on. You can predict the formula of any 2 or 3 elements mixing with one another. Just a quick note. The formula is a little bit misleading when it comes to ionic compounds. So ionic compounds themselves don't exist as kind of single molecules. So you don't really find, a single molecule of magnesium and oxygen, but rather they exist as large lattices. And we'll learn more about this later. Just want to introduce it. But for example, what I'm talking about here is let's have this orange circle represent an Na+, and then this purple circle represent a Cl-. Instead of just existing as one Na+ and Cl-, what it is, it's a whole bunch of them all grouped together, right? So in this case, opposite charges next to each other. And they exist in this three-dimensional huge lattice. All right, so maybe you find this simple, maybe you find this difficult. Either way, the best way to learn this is practice, right? It's not about watching videos. Learning is an active activity. So you're not going to learn through just watching. It's not, just osmosis. It's not just going to sink into your brain. You want to do some practice. So check out the work-alongs. If the work-alongs aren't enough, check out some online resources. And if you're still confused or struggling, you have a lot of resources, a lot of people that want to help you succeed. You can go see some tutors, or if you can make it to my office hours, I'd be more than happy to help you out as well. You have a lot of people that want to help you and want to help you succeed, but you've got to go ahead and take that first step.